I apologize for that. That obviously these things are recorded and weird things can happen. So let's back up. We're talking about angular momentum of a small object at a distance away from the orbits, from the center line of the rotation. So to end up finding the what your angular momentum is, you can use mr squared as being your moment of inertia because it's all at one radius. So then that your angular momentum will be mr squared times your angular velocity, and when you redistribute, your radius times your angular velocity of it moving here will be at speed. So it'll be the mass times the radius times the speed. Incidentally, here I didn't write it down. There's no special name for the unit for angular momentum, just like there's no special name for the unit of linear momentum. Uh, we'll often write it as a kilogram meter squared per second. Um, Another option, you can write it as a joule second. That we're not going to do very much where we end up needing that, but that might be if you are thinking about stuff that you learned way back in a chemistry class. Joule second may sound familiar because that is the unit for Planck's constant, and Planck's constant is in fact an angular momentum. We won't worry at all about that in this course because it's not a quantum course, but nevertheless. All right, so now we'll move to what I was planning on having as being the first topic of this next video, which was rotational collisions. If all of your significant torques are internal, angular momentum will be conserved. In this type of situation, one of the things that can happen, just like for linear momentum, is that can end up happening if you have a very rapid interaction. So then the internal torques are much larger than any of the external torques that are acting on the system. So over a short period of time, that will end up being true, even if it's not true in the long term. And so, as an example of how this can happen, let's suppose we have a bit of gum that's been spit out or whatever, and it ends up hitting, and what's going to hit is an object that's on a mount. So it ends up hitting it at a distance here away. So the length of the rod was 19 centimeters. It ends up hitting it 4.5 centimeters away from the edge, so it ends up smacking in there. The speed of the piece of gum was at 19.5 meters per second, so it was shot pretty fast. It's got a mass of 15 grams. It sticks to it, the whole thing has a mass. This bar has a mass of 114 grams. So we'll assume that the bar was initially at rest, so we find what the angular velocity of the system is whenever it sticks. So in this situation, that should sound familiar, except we're talking about rotation now instead of something that would stick and move laterally, which would be so in both cases, this would correspond to a perfectly inelastic collision. This is just a perfectly inelastic rotational collision instead of a perfectly elastic linear collision. So, same rule applies. The total in the old case, it was a total linear momentum at the beginning is a total linear momentum at the end. So now it's the total angular momentum at the beginning will equal the total angular momentum at the end. So we can end up computing that. So my angular momentum for the rod before it moves, it had no angular velocity. So your initial angular momentum is 0. And we end up using the formula we calculated. I was planning on at the end of the last one, but at the beginning of this one, MRV, we use that to find my initial angular momentum for the gum. So the mass times the radius, the distance. The radius is the distance from where the impact point was from the center times its speed at the impact. So you get 9.78 10 to the negative third kilogram meter squared per second. Um, then your final, they'll be, since it's stuck, they'll be rotating together. So then your final angular, final moment of inertia is the moment of inertia of the gum plus the moment of inertia for the bar. And for the gum, it's going to be mr squared because the mass, because it's still small. For a bar rotating through the center, the formula is in your table. It's 1/12 ml squared. So 1/12 times the mass times the length of the whole bar squared. So then you calculate what that number is, what your total moment of inertia is. And you end up with 3.73 10 to the negative fourth kilogram meter squared. So then we end up setting my total angular momentum at the beginning equal to total angular momentum at the end. And then solve for your final angular velocity. You get 26.2 radians per second. As a second example, that will have a person with a mass of 115 kilograms. That person is standing at 3.70 meters from the center of rotation of a carousel. So the person standing out here, where you're given the moment of inertia for the carousel is 475 kilogram meters squared. So person is initially at rest, so is the carousel. So then we assume the person starts to walk clockwise at 5.10 meters per second. What I want to do is find the angular velocity of the carousel whenever that happens. And in terms of understanding how to deal with this, we have to first account for the other possible external force. So if you have a person standing out here, there will be a torque, but the torque from there, the lever arm goes from the center point to where they're standing. The weight will be down, so the torque will not be along the axis of rotation. The torque is going to be perpendicular to it. And what the torque is going to try to do, if you're standing here, it should not be a trek. The torque will try to make it want to spin like this. So our assumption is going to be that our carousel will be built in such a way that it will end up canceling out whatever this torque is by another mechanism internal to this. But we'll end up also making the assumption that there's enough, so there will be effectively a normal force inside here. But we'll assume that it's sufficiently well lubricated that will end up not providing any significant friction against the rotation of the carousel. So there is a little bit of an assumption built in, but for us to be able to do a problem, we'll end up having to make that type of an assumption. So the rest of the problem, so now we're only dealing with the person walking or I said, wow, 5 meters per second, so running like hell. But anyway, the person will be moving around. So in this situation, when that would happen, for them to move, they end up having static friction against the surface. So they'll end up being friction against the carousel. And the carousel will also then have friction against the bottom of the feet because Newton's third law. So in this situation then, those forces, if we consider the person and the carousel together to be my system, those torques will be internal because the forces were internal. So even though there will be force, there will not be any external force. There will be torque, but no external torque. So in that scenario, then I will end up conserving angular momentum. So at that point, now we end up taking my total initial angular momentum will equal my total final angular momentum. And my initial angular momentum for the carousel is 0. The carousel started at rest. Person's was also 0. Person started at rest. So to be able to keep track of the person, we're assuming the person is, so I mean, 3 meters is a long way. So, that the person is not going to be very large compared with that 3.7 meters. So we will make the assumption the person is effectively a point out there at that distance radius away. So we can end up finding what, the person's the person's moment of inertia is going to be mr squared, and we already know how to find it if we know what the speed is. That will give me MRV. Now, again, MRV, you do have to be a little careful. It does have to be a point particle out there to use it. But if it is, then it's easy. We just multiply those together. That finds what my angular momentum is. Then I can use that to find what my final angular velocity for the carousel will be. Now, it should be clear if the person is going this way, that if the person is going this way, it's going to cause this to rotate the opposite way. So we end up having to choose a sign that's positive, and I'm going to end up choosing the counterclockwise direction, which would end up corresponding to coming out of the screen as being my positive direction. But notice if I do so, then the person's angular momentum will be negative. So we end up then calculating the negative MRV because of its choice of sign for the person, then plus my moment of inertia times the final angular velocity of the carousel. And I calculate then my final angular velocity is going to be 4.57 radians per second, and that will end up being clearly, it will end up going in the counterclockwise sense, the opposite way the person was going around. Okay? Then we are getting pretty close to the end of new material. The next bit of new material, which will be the last stuff that will be on both exam 3 and the final new material for the final exam, is going to end up being on it will be the concept sorry, the concept of equilibrium. So we'll be looking at what happens when we have both total force equal to 0 and total torque equal to 0 at the same time, and see some types of problems we can solve with that we couldn't end up solving with just one or the other.